Good afternoon. This is the third hour exam review. I'm going over selected problems that I saw that many people missed. This will not be a complete review, but just over selected problems. If I do not cover a problem that you have a specific question about from the exam, please make a time to come to my office and we'll get it addressed then. Starting off with problem number 13. Excuse me, number 9, sorry. It says the density of ammonia gas in a 4.32 liter container. The ammonia gas is at 837 torr pressure and 45 degrees C. It asks us what the density of that gas is. Hint, the value for R is 0.0821 liters atmospheres moles K. On help sheet number page, it has 28 on the bottom right of your exam. You see density is equal to the pressure, big italic M, the molar mass of the gas, R, the gas constant, 0.0821 times T. Well, we know the pressure. Pressure is 837, sorry. But since R is in units of ATM, we have to convert that to ATM. So 837 converted to ATM is 1.10 ATM. 1.10. Big M is the molar mass here. Avogadro's law says that, or Avogadro said that 1 mole of any compound is equal to sum of all the gram mass weights present of all the elements in that compound. So we've got 17 grams of the molar mass from nitrogen. 1 nitrogen is 14, 3 hydrogens are 3, 14 and 3 is 17. So the molar mass of nitrogen is 17 grams. R is 0.0821. Temperature is in degrees K, so we need to convert 45 degrees C to the corresponding value of K, 318.2 K. So the density is 1.10 times 17. All that divided by 0.0821 divided by 318.2. So the density here is 0.719, answer B. The next problem I'd like to review is problem number 13. Problem says the change in energy that a system experiences is equal to 12.4 joules of heat energy that are given off. In addition to the energy that the system releases in terms of heat, the system also does work. It changes something else. So the system is doing something. Not only is it losing heat, it's also performing some other task in the form of work. Therefore, since the system is causing something to happen, it is using up energy to cause that to happen. It is causing 4.2 joules of work to be done on the surroundings. So the total loss of energy is 12.4 joules due to loss of thermal energy and 4.2 joules of energy spent in terms of work, either changing the pressure of the system, changing the volume of the system. So it's doing something else on the surroundings. So the total amount of energy that the system lost is 12.4 plus 4.2, or minus 16.6. Again, the negative is looked at as energy lost. So since it's releasing 12.4 joules of energy and it's doing 4.2 joules of work, the energy is looked at as lost, so it's negative 16.6. Next problem I want to look at is problem 14. Which one of the following is an exothermic process? We have an endoskeleton. So to get to our skeleton and to be able to look at it, we have to go inside of our skin. So endo is system as energy is being added to the system. An exothermic process is where energy is being given away. So if we look at these, ice is melting. We are changing ice from the solid form to the liquid form. That is an endothermic process. We have to add heat to get the water to change from the solid phase to the liquid phase. Water evaporating. Here we're changing the phases from liquid to gas. That is an endothermic process. We have to add heat to that to occur. So ice melting is an endothermic process. Water evaporating is an endothermic process. If we boil soup, do you put soup when you're boiling it in a freezer or do you put it on the stove? Usually if you're boiling something, you're adding heat to it. Boiling soup is an endothermic process. Ammonium thiocyanate and barium hydroxide are mixed. And at 25 degrees C, the temperature drops. This is an endothermic process. Why? Because the temperature decreases. Therefore, to restabilize this, energy has to be added. Exothermic, heat is lost, given off. The only definition, the only answer here that fits an exothermic process, condensation of water vapor. Condensation is gas to liquid. So you're giving off energy. The vapor is giving off energy to condense down to the liquid phase. So answer here is D for number 14. Number 18. An 18.3 piece of aluminum having a specific heat capacity of 0.902 joules per gram per degree C is heated to 82.4 degrees and dropped into a calorimeter containing water with a specific heat of 4.184 joules per gram per degree C, initially at 22.3. The final temperature of the water is 25.8. Ignoring significant figures, calculate the mass of the water in the calorimeter. For problem 18, you have a piece of hot metal or metal that is at a higher temperature than the water it's going to be introduced into. So here we have our cup, here we have our water, and down at the bottom we have our hot metal aluminum. Because the aluminum is at a higher temperature than the water around it, heat energy is transferred from the aluminum to the water. How much heat energy is transferred from the aluminum to the water? Well, the amount of heat energy that the aluminum loses, Q metal, is equal to the mass of the metal specific heat metal and the temperature change of the metal. Well, do we know how much mass of the metal? Yes, 18.3 grams. What's the specific heat of aluminum? 0.902 joules per gram per degree C. What's the temperature change? The temperature was initially at 82.4 degrees C. The final temperature of the metal is the same temperature as the final temperature of the water because heat energy is continually transferred until the metal and the water are at the same temperature. So the temperature change that the metal underwent is from 82.4 to 25.8. So 82.4 to 25.8. 5, 7, nope. So 54.6. 6 and 8's 14, carry 1. 56. Okay, yes. So the temperature of the metal underwent a 56.6 degree C temperature change. So this is the amount of heat energy that the metal lost to the water. So it's 18.3 times 0.902 times 56.6. So 18.3 times 0.902 times 56.6. So the amount of heat energy lost by the metal was equal to 934 joules. Well, the heat energy lost by the metal, what did the metal lose it to? Well, the metal lost it to the water that it came into intimate contact with. So the only thing that the hot metal could transfer energy to was the water that it was in. So here's the water, the hot metal's in contact with the water, the hot metal is transferring energy to the water itself. The water absorbed the heat energy. How much heat energy? 934 joules worth of energy. So Q water is 934 joules is equal to the mass water times specific heat water times the temperature change water. 934 joules. It wants to know what the mass of the water is. We know the specific heat, 4.184 joules per gram per degree C. What temperature change did the water undergo? Initially, the water was at 22.3 degrees C. The temperature of the water increased, so it's 25.8. So the temperature change of the water was from 22.3 to 25.8. So the water underwent a 3.5 degree temperature change. It's asking us to solve for mass. So it is 934 divided by 4.184 times 3.5. So 934 divided by 4.184 divided by 3.5. So the mass is 934 joules divided by 4.184 joules per gram per degree C times 3.5 degrees C. So 934 divided by this, I get a mass of 63.8 grams of water. Next one I would like to look at is 25. you're given that frequency, nu, is equal to the speed of light divided by the wavelength. You're given the value of c being 3 times 10 to the 8th. So it's asking you the wavelength in nanometers of a frequency of light that has 3.2 times 10 to the 14th hertz. That's its frequency. So it is asking for lambda. So nu is equal to c divided by lambda. Therefore, multiplying through by wavelength by both sides, wavelength cancels out, so you have wavelength times frequency is equal to c. Divide both sides by frequency. Wavelength is c over frequency. C is 8.0, times 10 to the 8th meters per second. Over frequency. Frequency is 3.22 times 10 to the 14th per second. Doing that initial calculation, three times 10 to the 8th divided by 3.22 times 10 to the minus 14th. This gives us 9.38 times 10 to the 1, 2, 3, 4. 9.38 times 10 to the minus 7th. But this is in units of meters. It asks us for what the unit is in terms of nanometers. For every 1 meter, there is 1 times 10 to the 9th nanometers. So it is 9.38. Okay. 3, let me see. Let's check my math here. 3. 9.32. 9.32. So 9.32 times 10 to the minus 7th times this gets to 932 nanometers, which is answer number A. That was number 25 and number 32. Which ground state electron configuration represents a violation of Hund's rule for an atom in its ground electronic configurational state? Hund's rule says that when you have multiple orbitals that are degenerate having the same energy, electrons fill in like the p orbitals where we have 3, the d orbitals where we have 5. The f orbitals, where we have 7, where we have multiple orbitals that are degenerate, i.e. have the same energy, we say that the electrons occupy these orbitals singly first, such that you spin up electrons first, and then when each orbital has an electron, then you start spin pairing. So filled, filled, up, up, no electron, this is correct. Filled, filled, up, up, okay, both of these are correct. We usually fill from left to right, but this would be okay, just simply because we don't distinguish which is px, py, and pz. The accepted convention is that we mark from left to right, but we could write it this way. Filled, filled, up, up, okay. Again, these are occupied singly. It's not the convention. The agreed upon convention is that they go in with spin up. We can put them in spin down, but that's not how we generally are agreed to write these things. E, up, 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 no. This is a violation of Aufbau. Electrons fill in the lowest energy orbitals first and then start spin pairing. But this is not a violation of Hund's rule. This is a violation of Aufbau. D is a violation of Hund's rule. Spin up, down, spin up, down, spin up, down. No, this other electron should be here with spin up. So the electron orbital configuration that is not correct is number D. These are the problems that I saw people having. Most people miss these problems. If you have any other particular questions about any other problem that I did not cover in this video, again, please make an appointment to meet me in my office. Have a good afternoon. Thank you very much.